Okay, today's class is about reaction quotients. Reaction quotients are a way of calculating where a reaction is with respect to equilibrium. It is a number obtained by substituting starting reactant and product concentrations or partial pressures into an equilibrium constant expression. The resulting value allows one to make predictions about how the reaction will proceed. If you think of a chemical reaction like two springs pulling on one object, if you leave them alone, they'll stop moving and the object will stay in a certain position. If you think of a reaction that's not at equilibrium, it's like taking that object and pushing it to one side. What it'll do is put tension on one spring and loosen the other spring. But when you let it go, it'll oscillate back and forth, and eventually when it stops oscillating, it'll go back to the equilibrium position. With the reaction quotient, what we're allowed to do is predict which way the reaction is going to re-equilibrate. So we can tell if it's gone past the equilibrium point or if it's before the equilibrium point. At any rate, if Q is equal to K, the reaction is at equilibrium. If Q is bigger than K, the reaction will move left, and if Q is smaller than K, then the reaction will move to the right. An example from our textbook on page 646, Brown and others, 10th edition, says that sulfur trioxide can break down into sulfur dioxide plus oxygen. We're given initial conditions, or actually we're given the conditions of the reaction. We calculate Q the same way we would calculate the equilibrium constant, except the reaction is known not to be at equilibrium. Products of reactants. Remember that coefficients become powers. So the 2 next to the sulfur trioxide becomes sulfur trioxide to the power of 2, and the 2 next to the sulfur dioxide becomes sulfur dioxide to the power of 2. You enter the numbers, concentrations or pressures, whatever the case may be, and we get a number 16.41. If we continue on this board, we see that 16.4 is bigger than 0.338, which is the actual equilibrium constant, and this means the reaction is product rich, meaning it has gone further to the right than the reaction normally would be at equilibrium. So what we predict is that the action is going to re-equilibrate going towards the left. So it'll produce more SO3, which is one of the run reactant the reaction starts with. What is the purpose of knowing the reaction quotient? It helps us to predict what the reaction is going to do. Knowledge of the equilibrium constant makes it possible to predict the final concentration of reactants under controlled conditions. In another example, we are given 2 of the concentrations in the reaction, and the third one is left unknown, but we're also given the Kp value. So by entering all these values into the equilibrium expression, where that is again constituted by products over reactants, we attribute the value x to the unknown quantity, and then we simply solve it doing the algebra to find that the value of chlorine concentration is at equilibrium. In the third example, we use an ice table. This again is from your textbook, page 649. It shows phosphorus pentachloride breaking down into phosphorus trichloride and chlorine gas. We use an ice table. We are given the initial concentration of the phosphorus pentachloride, and we're given the value of Kp. At equilibrium, or not at equilibrium, rather, at the beginning of the reaction, there is no product, so we write 0. During the change, that is when the reaction is taking place, a certain amount x of PCl5 breaks down, and the same amount of moles, or pressure, x, of PCl3 forms, as well as Cl2. That's all we know. By setting up an equilibrium where 0.497 is equal to concentration of products over reactants, where PCl3 and Cl2 are the reactants, we can substitute these molecular symbols for numerical quantities that we have attributed a variable to. So x by x over 1.66 minus x, we get a quadratic formula, plug in the numbers, and the final result is 0.693. You're going to get 2 values when you solve this equation. One of them is negative, so you're going to discard it because you can't have a negative concentration. And this value, 0.693, is equal to x, so it equals to the concentration of PCl3 and Cl2. It also helps us to find out what the remaining concentration of PCl5 is. So 1.66 minus the value of x will give you that at equilibrium. We have 0.967 atmospheres of PCl5 and 0.693 atmospheres of PCl3 and Cl2.